In my last video, I built a Z-axis for my new CNC machine, but I didn't connect it to a motor because I wanted to talk a bit about limit switches and homing first. It's best to think of three different kinds of limit. This red line shows the absolute or mechanical limits of the machine. The machine cannot physically move outside of these limits, but unless the machine knows where it is, there's nothing to stop it from trying, and this might damage the machine. We want to avoid ever getting to this red line. This yellow line shows the points of the machine where we're going to place the limit switches. When the machine reaches these points during automatic movement, it should stop immediately, and control should return to the operator. Touching these limits is generally an error state. These limits need to be close to the red line to maximise the work area, but not so close that the machine can't come to a full stop in time. This green line shows the points of the machine where we can move safely, and this soft limit area is defined with reference to a known home point, which is also defined by the position of a limit switch. When we turn the machine on, we need to instruct it to first find the home point, and once we've found the home point, we know where the edges of that green box are, and the machine can try and stay inside that area. Here are some mechanical limit switches and an optical limit switch. The mechanical ones can be wired together very simply. If I attach one to an input pin on the parallel port and connect the other end to ground and then actuate it, you can see the state change. There is a small problem here though. If we want limit switches on the ends of all three axes, and a home switch on each axis too, we'd need 9 parallel port inputs, but we only have 5 available. One thing that might not be obvious immediately is that we don't really need one input for the end of each axis, because we only intend to return control to the operator whenever we hit a hard limit. So we only need to know that a hard limit was reached, rather than which one was reached. So we only really need to consume one input for all of the 6 hard limits. Also, as long as the machine is only moving in one axis at a time, and because the machine always knows which direction it's moving in, we can in fact tell which switch we're hitting, as long as we're moving in only one axis. We could use this to home all 3 axes using only one input as well. We just need to tell the machine to home one axis at a time. During the homing cycle, the machine moves in one direction slowly. If we get to an input that's a home switch, then we know it can only be the home switch on the axis that we were moving on. If we hit a limit switch instead, we'd know that we've missed the home switch, and we need to search in another direction for it, because we could only have hit the limit switch in the direction that we were moving in. To combine multiple limit switches, and make sure that we only use one input for home and one input for limits, the easiest way with simple mechanical switches is just to wire them together in either series or parallel. To avoid a floating input, which could be susceptible to electrical noise, I would pull up the input pin to 5 volts with a moderately sized resistor. This means that the input is well defined as either 5 volts or ground. When any one switch is changed, the output state changes. It doesn't matter much that the output states are different with these 2 options, because we can invert the meaning of an input in LinuxCNC. And limit switches are usually single pole double throw switches, so we can wire them as normally open or normally closed. There is a slight problem with these simple approaches though. All switches have a bit of bounciness. That means when actuated, for a tiny amount of time, the switch might be in an indeterminate state and rapidly changing between being connected and not connected. We can get limit switches on ready-made modules like these, and these modules have their own individual pull-up resistor and a noise filtering capacitor. With these modules, we can't just tie all the signal pins together, because if we did, we'd short 5 volts to ground whenever a switch is pressed. We need to think of these modules as more like TTL logic inputs than simple switches. To combine logic inputs, we need a multi-input AND, not AND, or even or not or gate. I designed this input aggregation circuit to help with this. There is a diode for each of the home inputs and a MOSFET transistor for the home output. As long as all of these home inputs are at 5 volts, then there's no potential difference across any of the diodes. So power is going to preferentially flow to the gate of the MOSFET, which will activate it. If the MOSFET is active, then power is going to flow through that instead of flowing through the home output. Now if any one of these inputs becomes ground, which happens when the switch is actuated, now there's a potential difference across the diode, and power is going to preferentially flow through the diode to ground on the actuated switch, which means the MOSFET will turn off, which means now power will flow to the home output. I also added an indicator LED to each of the inputs, so that I can see from the aggregation board which switch has been activated, in case it's not obvious by looking at the machine itself. I laid out this board in KiCad with mounting holes for standard DIN rail, which is what I'm going to standardise on for the wiring of this machine, and then send it off to JLC PCB for manufacturing. I had them make the PCBs and solder all of the SMD components, so the only thing I had to do was hand solder these terminals. I also had JLC PCB build me these limit switch PCBs to fit the small limit switches that I have. They have the same pull-up resistor and filtering capacitor as in the schematic that we looked at earlier. These are a version 1 design. I've already modified the design and ordered version 2, because I left such a small gap here between the wiring points. I'm not that great at soldering and I've destroyed 2 of these already. Eventually I'm going to drill and tap holes into the Z-axis plate to attach these limit switches. For now though, I just 3D printed these interference fit carriers so I can align everything first, and once I'm happy with the position of everything, I will use them as drilling guides. As I mentioned earlier, I'm going to standardise on DIM rail for the electronics of this machine. Luckily, a lot of modules already come with the correct hole spacing, and I've cut some DIM rail adapters for my motor drivers from aluminium strip. These terminal blocks are pretty handy for splitting connections when required, although they are a little bit bulky. Here's how everything looks wired up. It's a little bit messy at the moment. I'm going to have to cable manage this a bit better. It could definitely be a bit tidier. We have a limit switch here, a limit switch here, and a limit switch in there that I can't quite reach. The signal line for each of these limit switches is wired up to the respective Z pins on the aggregation board. We have the DB25 connector wired up to the motor driver, like shown in the first steps for LinuxCNC video, and then we have the outputs from the signal aggregator board also connected to the DB25 port. Because we need 5 volts for this new module, I've got a little 5 volt DC to DC converter here, and then 12 volts is going to the motor driver. This is how I've configured the machine in StepConf. The only important pins are the Z step, Z direction, and the all limits and all home pins. In my case, I had to invert the meaning of the all home pin. I've also configured the Z axis to fit the actual size of my machine. It's got travel from 0 to minus 120mm, and my home switch is 10mm away from the home location, down towards the travel direction. I also had to invert the home search velocity, or it would try and search in the wrong direction. Let's fire up the axis interface for the mill, and disable the emergency stop and turn the machine on. At the moment, I'm not really respecting these buttons in hardware, which is pretty dangerous on a real machine, but for now this is fine and we'll deal with that later. If I pick the Z axis now and change the jog speed, I can now move in either direction. Unfortunately, when we reach our limit switch, although we do stop, which is better than carrying on, we never wanted to get to a situation where we're stuck on a limit switch. We want to use the soft limits instead, and to do that we need the machine to find the home position. To get out of this situation where the machine is stuck on a limit, you can override the limits, turn the machine back on, and then you can move off the problematic switch. If we now home just the Z axis, very slowly and very noisily, we moved up towards the home switch, activated it at minus 10mm, and then moved from the home switch up to the home position, which is at 0mm. Now if we try to move, when we get down to minus 120, the machine isn't moving any further. I can't command it to move in that direction anymore. But we didn't hit the limit switches this time, which is good. There's no error state, and we don't have to override limits to keep going. We can go back up to the home position, and that's it, we've got a homed axis now. That is, we're moving within the soft limit area that we defined. If I unhome the axis now, that puts it back into a state where we no longer have a soft limit area. If this time, I start homing whilst already on the home switch, you'll see the machine move down this time until the home switch is no longer active, and then resume searching upwards, and then we're homed again. I placed my home switch very close to the hard limit deliberately, so that wherever I start homing from, I'll always be able to home successfully without hitting a hard limit. This is what I wanted to do in this video. Next time, I'll either be working on the other axes of the machine, or working on respecting the emergency stop and machine power state in hardware.